It was on a day like today that I started to question the effects the cold weather was having on my tire pressure. You gotta figure, from plus 23 degrees indoors to minus 18 outdoors, that's 41 degree temperature. How does that affect tire pressure? Right? To begin, I need to know how much air is in the tire. When you think about it, the bike wheel is basically just a big donut shape. In math and physics, we call this a torus. This will be my control volume. We'll consider it to be rigid. The volume contained within the torus can be calculated using the equation V equals pi small r squared times 2 pi big R. Where the small r is the radius of the tire, and the big R is the radius of the rim. If you analyze this equation, it's really just the cross-sectional area times the circumference of the wheel. So the volume of a torus is perhaps intuitively just the cross-sectional area times the circumference. Specifically, the circumference of the central axis of the torus. Now we call it a 26-inch wheel. Well, what does that really mean? What are inches anyways? If you've ever tried installing a 26 by 1.5 inch tire on a 26 by 1.5 inch rim, or if you've ever wondered why a 27-inch wheel is bigger than a 29-inch wheel, or the 27.5 inch is smaller than both 27 and 29, well then you might have been puzzled by the bicycle industry's quirky wheel sizing. Right? Fortunately, back in the 1960s, the European Tire and Rim Technical Organization was established to harmonize these standards. Now, as we kicked into the 1980s, the International Standards Organization got involved. They came out with ISO 57751 and ISO 57752. These established tire and rim interferences. So my 26 by 2.5 inch trials wheel is more properly known as an ETRTO 559-64. This means that it has a 559mm bead seat diameter and a 64mm tread width. The volume equation for the torus requires the wheel's radius to be the central axis of the tire itself. The central axis of the wheel diameter will be the bead seat diameter plus half the tire width. So that's 559mm plus 32mm. That's 0.00597 cubic meters, or 5.97 liters. Interesting. That's the volume of space within my tire. If I were filling my tire with water, that's exactly how much water I would fit in it to fill this volume. But unlike water, the air in my tires is easily compressible, and 6 liters of air would only fill my tire to atmospheric pressure. But at 0 gauge pressure. Before I left the house, I filled my tire to 25 psi. That's 172.369 kilopascals. Now that's gauge pressure. The ideal gas law that I'm about to use is based on absolute pressure. To start, the atmosphere alone's at about 101.3 kilopascals. Add to that, my 172.3. The atmosphere alone's at about 101.3 kilopascals. Add to that my 172.369 kilopascals of the tire inflation pressure, and you end up with 273.669 kilopascals of absolute pressure. So how much air does it take to fill a 5.9729 liter container to 273.669 kilopascals, or 39.7 psi? much air did my air compressor actually have to cram in there to bring it up to 25 psi gauge pressure? This is a non-flow process where the air is at relatively low pressure. It behaves as an ideal gas. I can analyze its parameters using the ideal gas law. KV equals MRT. E is the pressure of the air. V is the volume of the tire. M is the mass of the substance in kilograms. R is the ideal gas constant, and it's unique to each gas. And T is the temperature of the gas in kelvins. Rearranging the ideal gas law to isolate for M, I get M in kilograms equals PV over RT. That's 19.23 grams of air to fill my tire to 25 psi. That's nearly 40 grams of air in the bike. Wait, so if I let all the air out of my tires, my bike will get lighter? Yes. That's right, all that air is just weighing you down. But it does ride better with some air. Maybe worth the added weight. Needs more air. But I would do anything to save a gram.
A few moments later.
After an extended time riding in double-digit negative temperatures, the air in my tires has reached thermal equilibrium with the outdoor air. The air in the tire now matches the negative 18 degrees Celsius ambient temperature outdoors. That's a 41 degree temperature difference from where it started. Now, the amount of air in the tire has not changed, but the temperature of the air has dropped. Knowing how much air is in the tire, 0.01923 kilograms, I can rearrange the ideal gas law to isolate for P and see how much the pressure changes with dropping temperature. So at minus 18 degrees Celsius, the pressure in my tire will have dropped to 235.78 kilopascals. Now that's absolute pressure. Subtract an atmosphere of 101.3 kilopascals, and you end up with 134.5 kilopascals, or 19.5 psi, of tire gauge pressure. And that's it. Without changing the amount of air in the tire, the pressure dropped 5.5 psi. And it's true. This is why I wasn't landing much this winter. How much heat energy was lost to the atmosphere for my tire to drop that 5.5 psi? It took work to warm the air in my house up to 23 degrees Celsius on a cold winter week. How much heat energy was transferred to the atmosphere from the air in my tires that day? the CV for air is 0.718 kilojoules per kilogram Kelvin. That's 565.5 joules of heat leaving my system to the surroundings. And what's the effect on entropy? First, recall that entropy is a measure of the amount of disorder within a system. It represents an unavailability of energy within a closed system. High entropy state is a higher state of disorder, while a low entropy state entails a higher concentration of energy. I treated my tire as an isolated control volume. However, obviously it conducts temperature to the environment. When considering entropy, I considered the closed system as including the atmosphere that the tire is exposed to. In this case, I recognize that the concentration of energy is dispersed to the atmosphere. The energy is in a higher state of disorder, and there's been an increase in entropy. So I quantify it. It's a constant volume process, an isochoric process. And with no change in volume, there's no boundary movement, thus no boundary work. So W work equals 0. For a constant volume process, the change in entropy, delta S, equals CV times the natural log of T2 over T1. This process resulted in an entropy increase of 11.88 joules per Kelvin. The universe is heating!